We all heard space buffs talk about these Lagrangian points. I mean, the James Webb Space Telescope is sitting comfortably at the L2 Lagrange point, but what is that, and more importantly, where is that in space? Well, today we'll discuss this concept and explain where a Lagrange point is, what it is, and also who discovered it. So, stay tuned on this episode of Space Definition, as we explain everything about Lagrange points, and be sure to like this video if you enjoy it and subscribe to this channel, as we are new to YouTube and would like to grow, so please share this video with your friends and family, as we go into detail explaining another space definition on the Rocket Center. As you would imagine, the Lagrangian points were named after a person called Lagrange or something like that, but I guess this time you would be wrong, because the first person who discovered the Lagrangian points was called Leonhard Euler. He was a Swiss mathematician and he discovered them in 1750. He discovered the first 3 points, L1 to L3, and only a decade later the Italian-born Joseph Louis Lagrange discovered the remaining 2. In 1772, Lagrange published an essay on the three-body problem. In the first chapter he considered the general three-body problem. From that, in the second chapter, he demonstrated 2 special constant pattern solutions, the collinear and the equilateral, for any 3 masses, with circular orbits. Well, now that you know who discovered the Lagrange points, let's explain the what part of this topic. So, a quick search on Wikipedia tells me that Lagrange points are points of equilibrium for small mass objects under the gravitational influence of 2 massive orbiting bodies. But I don't know about you, but that really didn't explain much for me, so I'm going to try explain it in simple terms. Lagrange points are special points in space where the gravitational forces of 2 large objects, like the Sun and the Earth, create regions of balance. These points allow smaller objects, such as satellites or spacecraft, to maintain a stable position without using a lot of fuel to constantly adjust their orbits. There are 5 Lagrange points, L1 to L5, all in the orbital plane of any 2 large bodies. There are 5 Lagrange points for the Sun-Earth system, and 5 different Lagrange points for the Earth-Moon system. Each point has its own unique characteristics and is located at different positions relative to the 2 large objects. These points have been used for various purposes, such as space exploration and satellite positioning, like the James Webb Telescope we just mentioned earlier. When the mass ratio of the 2 bodies is large enough, the L4 and L5 points are stable points, which means that objects can orbit them like stable parking spots, where objects can stay in orbit without being pulled towards one object or the other. Imagine 2 large objects, let's say planets, and you have a smaller object like a spaceship. If the mass ratio between the 2 planets is large enough, then the L4 and L5 points become stable points. This means that the spaceship can orbit around these points without being pulled towards either planet, almost like tug-of-war between planets, and neither one is strong enough to beat the other, and the spaceship is the knot in the center of the rope. Several planets have Trojan asteroids near their L4 and L5 points. With respect to the Sun, Jupiter has more than 1 million of these Trojans. As you would guess, Trojan asteroids are just asteroids that wandered too close to these planets and were caught in these L4 and 5 points. 2 important Lagrange points in the Sun-Earth system are L1, between the Sun and Earth, and L2, on the same line at the opposite side of the Earth. Both are well outside the Moon's orbit. Currently, an artificial satellite called the Deep Space Climate Observatory is located at L1 to study solar wind coming toward Earth from the Sun and to monitor Earth's climate by taking images and sending them back. And the James Webb Space Telescope, a powerful infrared space observatory, is located at L2. This allows the satellite's large sun shield to protect the telescope from the light and heat of the Sun, Earth, and Moon. By the way, an artificial satellite is an object, typically a spacecraft, placed into orbit around a celestial body like the Earth or the Moon, but the Moon is a natural satellite of the Earth. There is a difference, and maybe we'll discuss that in another video. The European Space Agency's earlier Gaia telescope, and its newly launched Euclid, also occupy orbits around L2. each of. The space observatories benefit from being far enough from Earth's shadow to utilize solar panels for power, and from not needing much power or propellant for station keeping, and from not being subjected to the Earth's magnetospheric effects, and from having direct line of sight to Earth for data transfer. Now let's discuss each Lagrange point and each of their special characteristics, starting first with the L1 point. The L1 point lies on the imaginary straight line between the two large masses M1 and M2. It is the point where the gravitational attraction of M2 and that of M1 combine to produce an equilibrium. An object that orbits the Sun more closely than Earth would typically have a shorter orbital period than Earth, but that ignores the effect of Earth's gravitational pull. If the object is directly between Earth and the Sun, then Earth's gravity counteracts some of the Sun's pull on the object, increasing the object's orbital period. The closer to Earth the object is, the greater this effect is. At the L1 point, the object's orbital period becomes exactly equal to Earth's orbital period. L1 is about 1.5 million kilometers, or 0.01 AU, from Earth in the direction of the Sun. Just to make sure we're on the same page, an AU is an abbreviation which stands for astronomical unit. It is the ruler that scientists use to measure distance in the solar system. It's the average distance between the center of the Earth and the center of the Sun, which is 150 million kilometers, or about 93.2 million miles. They use the average distance because the actual distance varies depending on the time of year, because the Earth's orbit around the Sun is not a perfect circle. Fun fact, the universe is estimated to be 93 billion light-years across, and in AU, it'll still be 5.85 billion AU across. That means you'll need 5.85 million AUs to measure the universe. But I digress. Now let's explain the L2 and L3 points. The L2 point lies on the line through the two large masses beyond the smaller of the two. Here, the combined gravitational forces of the two large masses balance the centrifugal force on a body at L2. On the opposite side of Earth from the Sun, the orbital period of an object would normally be greater than Earth's. The extra pull of Earth's gravity decreases the object's orbital period, and at the L2 point, that orbital period becomes equal to Earth's. Like L1, L2 is about 1.5 million kilometers away from the Sun. The L3 point lies on the line defined by the two large masses, beyond the larger of the two. Within the Sun-Earth system, the L3 point exists on the opposite side of the Sun, a little outside Earth's orbit and slightly farther from the center of the Sun than Earth is. This placement occurs because the Sun is also affected by Earth's gravity and so orbits around the two bodies' barycenter, which is well inside the body of the Sun. The barycenter is the center of mass of two or more bodies that orbit one another and is the point about which the bodies orbit. A barycenter is a dynamical point, not a physical object. An object at Earth's distance from the Sun would have an orbital period of 1 year if only the Sun's gravity is considered. But an object on the opposite side of the Sun from Earth and directly in line with both feels Earth's gravity adding slightly to the Sun's and therefore must orbit a little farther from the barycenter of Earth and Sun in order to have the same 1 year period. It is at the L3 point that the combined pull of Earth and Sun causes the object to orbit with the same period as Earth, in effect orbiting an Earth plus Sun mass with the Earth-Sun barycenter at one focus of its orbit. Now for the L4 and L5 points. These points are located at the third vertices of two equilateral triangles formed by the orbital plane of the two masses. The line connecting the centers of the masses serves as the base of these triangles. The L4 point is positioned 60 degrees ahead of the smaller mass in its orbit around the larger mass, while the L5 point is positioned 60 degrees behind. These points are stable because the gravitational forces from the two masses balance out, allowing objects to maintain their positions without drifting away. In simpler terms, imagine two objects in space, like the Earth and the Moon. The L4 and L5 points would be like special spots where a smaller object could stay in place, almost like it's sitting in a little pocket of gravitational balance. It's like finding a sweet spot where the forces from the Earth and the Moon cancel each other out, allowing the smaller object to stay put. Fun fact, these 2 points are the most ideal Lagrange points for artificial space habitats like the O'Neill cylinder. An in-space habitation designed to be large enough to house a self-sustaining human population and provide a comfortable living environment for millions of people. Maybe we'll discuss this topic as well in another video. Now let's discuss various spaceflight applications for Lagrange points. The Sun, Earth L1 is suited for making observations of the Sun-Earth system. Objects here are never shadowed by Earth or the Moon, and if observing Earth, always view the sunlit hemisphere. The first mission of this type was the 1978 International Sun-Earth Explorer 3 mission, used as an interplanetary early warning storm monitor for solar disturbances. Conversely, it is also useful for space-based solar telescopes, because it provides an uninterrupted view of the Sun, and any space weather, including the solar wind and coronal mass ejections, reaches L1 up to an hour before Earth. By the way, the solar wind is a stream of charged particles released from the upper atmosphere of the Sun, called the corona, and a coronal mass ejection, or CME, is a significant ejection of magnetic field and accompanying plasma mass from the Sun's corona into the heliosphere. CMEs are often associated with solar flares and other forms of solar activity. Planned missions to the L1 point include the Interstellar Mapping and Acceleration Probe, or IMAP, India's Aditya L1 mission, and the NEO Surveyor. The Sun, Earth L2 is a good spot for space-based observatories because an object around L2 will maintain the same relative position with respect to the Sun and Earth. Shielding and calibration are much simpler. It is, however, slightly beyond the reach of Earth's umbra, so solar radiation is not completely blocked at L2. Spacecraft generally orbit around L2, avoiding partial eclipses of the Sun to maintain a constant temperature. From locations near L2, the Sun, Earth and Moon are relatively close together in the sky. This means that a large sunshade with the telescope on the dark side can allow the telescope to cool passively to around 50 Kelvin or -223 degrees Celsius. This is especially helpful for infrared astronomy and observations of the cosmic microwave background like the James Webb Space Telescope. A spacecraft orbiting near Sun, Earth L3 would be able to closely monitor the evolution of active sunspot regions before they rotate into a geo-effective position, so that a 7-day early warning could be issued by the NOAA Space Weather Prediction Center. Moreover, a satellite near the Sun, Earth L3 would provide very important observations not only for Earth forecasts, but also for deep space support like Mars predictions and for crewed missions to near-Earth asteroids. The Earth-Moon L1 allows comparatively easy access to lunar and Earth orbits with minimal change in velocity, and this has as an advantage to position a habitable space station intended to help transport cargo and personnel to the Moon and back. The Earth-Moon L2 has been used for a communications satellite covering the Moon's far side, for example, Keiqiao, launched in 2018, and would be an ideal location for a propellant depot as part of the proposed depot-based space transportation architecture. The Earth-Moon L4 and L5 are the locations for the Kordylewski dust clouds. Kordylewski clouds, also named ghost moons, are concentrations of dust in these areas. Scientists at the B612 Foundation were planning to use Venus's L3 point to position their planned Sentinel telescope, which aimed to look back towards Earth's orbit and compile a catalog of near-Earth asteroids. Exploring the universe is full of surprises and wonders. Keep questioning, keep learning, and keep reaching for the stars. Remember to hit the like button and subscribe to catch the upcoming content.